Hello, welcome back on today's lecture. Today we're going to talk about how we can measure dependencies. Like let's say you have two random variables and you want to measure how dependent they are with either correlation, covariance, as well as mutual information. I'm Professor Wu, so let's get started. In science, we often need to study the relationship between two factors. In this plot, for example, we have income versus health of an individual. And you can see that in general, there's a positive trend that as income increases, the health also increase, essentially saying that richer people tends to be healthier according to this plot. Here's an example. So that was called a positive correlation. A positive correlation. Now, a positive correlation implies that as one increases, other also increase. Now, opposite of a positive correlation is called a negative correlation, which means as one increases, the other decrease. Notice it's decreasing, right? So in this particular case, we're measuring the amount a person exercises versus their heart rate. So what this is saying is that as a person exercises more and more, their resting heart rate goes lower and lower, which implies they're healthier. So this right here is a negative correlation because it's going lower and lower, which is in this case good. Here's another example of a positive correlation where one goes up, the other one also goes up. The more sugar you have, the more likely you're going to have tooth decay. So, like with these kind of relationships, by looking at the plot itself, we can essentially figure out the kind of relationship. Something that looks like this is positive, and it's a linear relationship because a line can do a pretty good job describing the relationship. Over here is also linear, but this time it's negative because as one goes up, the other goes down. And over here, it's also negative. However, instead of a line, like a linear relationship, what we have is a curve. So it's no longer linear, it's actually nonlinear. And this one is an example of no relationship. All right, so a way that is measured in the dependency between two variables is called covariance. Covariance is a way of measuring dependence. So over here is an example of a high covariance, so high dependency. You see how one goes up. It's very obvious that the other also goes up. And over here is an example of low or no dependency because as one goes up, well, it's all over the place. It doesn't mean it's going to go up. It doesn't mean it's going to go down. So high dependency, no dependency. And covariance is a way of measuring that. If I actually calculate the covariance for this one, notice I got a big number, whereas this one is close to zero, right? It's a very low dependency. So covariance, by calculating this value, you can essentially look at the value and figure out whether two variables are highly dependent of each other or not very highly dependent of each other. Now, the equation for covariance looks very similar to variance. So we previously learned variance, right? Variance is the distance from the center square and then average. So it's the average distance from the center square. And therefore, when we multiply them together, right, it's the distance from the center square, like twice. So the covariance equation looks very similar. So covariance is just x. Covariance takes two variables into account. When you take two variables into account, then what you have is the distance from the center for x and the distance from center y multiplied together and the average of that. So it's the average of the distance from the center for x times the distance from the center for y. And notice how the covariance equation looks very, very similar to the variance equation. Okay? So for the case of population, we have 1 over n, and empirical, we have 1 over n minus 1. So the equation between covariance and variance is very, very similar. What is interesting is if you have covariance with itself, right? Notice how covariance x and x, right? Previous is x and y, but if x is equal to y, then covariance breaks down back into variance again. So covariance is just variance with like something compared to something else. The equation of covariance and variance are very, very similar. All right, so this is the equation we're looking at, not this one. This one. This is the equation we're looking at. And if you just look at it, you might wonder to yourself, how is this equation measuring variation, right? So over here, how is the distance from the center for x times distance from the center for y multiplied together going to give us dependency? So how does that happen? Well, it has everything to do with the plot. So as I said, this is an example of a strong dependency. Therefore, strong dependency will look like this. A weak dependency will look like this, right? And a negative dependency will look like this. So you are gonna get a strong, large positive value, and over here you're gonna get like close to 0, and over here you're going to get like a strong negative value, right? So how does the equation work? Well, okay, let's look at this equation. I'm going to write the equation right here. So it's 1 over n xi minus mu x yi minus mu y. Okay, so that's the equation. So from this plot, we can figure out the center point. So this point is basically mu x. That's the middle point. And this point is mu y, right? Now, as we go through the list of x1, x2, y1, y2, so on and so forth, the pairs, right? x1, x2, x2, y2. As we go through this pair, let's say we pick a point that is above x1, is above the mean. What's likely going to happen? Well, what's likely going to happen is that the y value, y1, is also above mu y. So if x is larger than mu x, x1 minus mu x must be a positive value. And when this is also larger, you have y1 minus mu y. This is also positive, right? Notice how y1 minus mu y is a positive value, resulting in a positive. Multiply them together leads to a positive value. Conversely, if the value is right here, x2, right? If x2 is below the average, then y2 is also likely to be below the average. If it's below the average, you will get a minus, leading to a plus. This kind of tells you that because of the shape of the positive dependency, that when you have a value xi that's above the average, it implies that the y is likely to be also above the average, giving you positive. Because of the shape, if it's below average, it's likely that the y value is also below average, also giving a positive. So in the end, when you multiply them together, bunch of samples, and sum them up, if they are largely positive, then this is going to be a large positive value, right? So this is why this right here, you can intuitively see that how we can get a large positive value when you multiply the two equations together, right? The average from x times the average from y, okay? Now, this same relationship doesn't hold when we have just noise. This right here is pretty close to noise, right? So you can see that this is the average x mu x, and this is the mu y. Now, if you just look at here, if you point x1, right? So when you have these x1, it's not more likely that y is going to be here. Instead, y could be here, 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 here. So notice some of them are positive, some of them are negative. Therefore, when you sum them together, xi minus mu x, yi minus mu y. When you sum them together, some are going to be positive, some are going to be negative, positive, negative, and they cancel each other out towards 0. And this is why when you have shape that looks like this, you're going to get 0 or close to 0, a small number, because the positive and the negative cancel each other out. Conversely, if we look at the last situation where we have a strong negative, and this also makes sense, because if we just pick the center point, so the center point is somewhere here, so this is mu x, mu y, right? Well, if we have an x value that is greater, so xi minus mu x, if it's greater, then it's going to be positive. But whenever this is greater, you're more likely to see that yi is going to be lower than mu. So therefore, yi minus mu y, this is likely to be a negative. Therefore, notice how these values are all going to be negative. And these values, similarly, it's saying that mu y, if the x values are below xi mu of x, xi values are below, this is going to be less than, right? Because this is below the average. But whenever it's below, it's more likely that the y values are above, still giving you negative. So the summation of all these negative values give you a strong negative. And this is the intuition of why this equation works, by looking at the shape. If you just look at the shape, that's exactly what's happening. With certain shape, you will have a certain characteristic. Positive, strong negative. All right, so at this point, I want you to pause the video, run these practice, make sure you can calculate this yourself, okay? Here's the solution that you get to look at. Okay, so now that we've learned the concept of covariance, covariance is great because we know positive is good. It's a positive relationship. Negative is a negative relationship. However, the actual value itself is not very clear. If we look at the first number, right, x and y, in the second data set, the only difference is I multiply x by 100. Well, notice that when we measure dependency, suddenly the dependency of larger numbers are just larger, whereas the dependency of small numbers are smaller. So sometimes the dependency may not necessarily be large, it's just because the number themselves are very large. And therefore that is a major flaw of covariance. That the positive, negative, and 0 are great, but we don't really know what good or a strong positive really look like. Okay, so because it could look at the variation between these two, it's very large, right? And this could be a small, and this could be a large dependency. So the concept of magnitude, large, is kind of lost in covariance. Covariance only really give us signs, positive, negative, and 0. So to fix this problem, what we like to do is scale covariance into a certain range. Okay, what we like to do is maybe take the covariance, divide by some number. And by dividing this number, we can guarantee that the result is always between -1 and 1. And that is great because if that's the case, if I tell you -0.98, then we know this is a very strong negative relationship, right? If we say 0, then it's 0. And if I say 0.99 positive, we also know this is a strong relationship. So scaling them between -1 and 1 is very, very useful. So after we take covariance and divide it by some number to scale them, this term right here is called a correlation. Correlation. Okay. So once we convert it into a correlation, we know the scale and we know how this works. So the key is, what is this number, right? We now know how to calculate covariance, but then how do we know what number we should divide it by? Well, how do we do that? Well, all we have to do is make a couple observations. First observation is that covariance of x and y the dependence between two variables has to be less than the dependence with itself. You cannot depend on anybody else more than you can depend on yourself. Okay. Similarly, this is xx. The covariance must also be less dependent than itself in terms of y. So it's in terms of x, in terms of y, both the dependence between x and y must be less than. Okay, you cannot depend on anybody else more than you depend on yourself because you are perfectly in accordance with yourself. At least that's what we try to do. So if this is the case, we can now divide this by this, and it has to be less than one. If we divide this by this, because if you simply divide them, we have this observation that the covariance of xy divided by covariance xx is less than one, and the covariance xy divided by covariance yy is also less than one. So this is observation one. The second observation that we need to keep in mind is that if you have two numbers that are less than one and we multiply them together, it's still less than one. So, like, take this, right? This is less than one, we multiply them together, it's still less than one. So, that's the second observation. Number two, number one, number two. Number three is that the square root of the value less than one is still less than one. Okay, if we take square root of any number less than one, the result will still be less than one. Now, if we combine these three logic together, we would say that, well, if this is less than one, this is less than one, we multiply them together, the result must still be less than one, which is the first observation we make. If this is less than one, this is less than one, we multiply them together, this inequality must be true. Okay. Well, after we multiply them together, then it's covariance square, right? What we can do is we can take the square root, because if this is less than one, the square root of this must still be less than one, like such. Well, this part is square, right? This part is square. Therefore, the square cancels out so that this could be positive or negative, right? So now what's happening is we take the square root of this, and now we have the square root of the bottom. Therefore, we now know the number we divided by. If we divide it by this, it gives us correlation. Well, this is the relationship we just saw. This is how we get correlation. But we're going to make one more adjustment. Right? Remember that covariance of xx, right, is simply the variance of x, and the covariance of yy is simply the variance of y. So what we have, the final form for correlation, is the covariance, and we need to divide by some number, right? And the number is simply the variance of x times variance of y, divide a square root. Okay, so that is the equation for correlation. And I expect you to remember this. All right, so let's do a quick practice. Like, pause and see if we can calculate the correlation with this by hand. Well, as much as you can by hand. So pause the video. We're going to move on. Okay, so hopefully you're able to get the right solution. Now, when we practice calculating correlation, you can also do this in NumPy. So let's say we have two variables, x and y. Notice that we can call NumPy covariance or correlation coefficient for this. However, it didn't generate a number. Instead, it generates a matrix. Why is that? It's because this is actually called a covariance matrix. So when we are trying to calculate the covariance of x and y, it generates a matrix where you have covariance of xx, covariance of xy, covariance of yx, and covariance of y. That's why you have a matrix, because it automatically generates every combination for you. The similar idea follows for correlation. It also gives you a matrix because it essentially scale each one of them for you. Okay. All right. One quick note about correlation. High correlation does not imply causation. So here's an example. Here is the total number of ice cream sold, and here is total number of drowning. We can see a clear positive dependency. But can we then say that the ice cream being sold is causing the drowning? And the answer is no. You cannot say that total amount of ice cream sold and is causing it. In this particular case, we have a third factor called the hot weather. The hot weather is causing the more amount of ice cream sold, as well as more people going to the beach, implying drowning. So just because two factors are highly dependent on each other, you can't automatically assume that one of the factor is causing the other factor. You might have a third factor, which is called a confounding factor. Okay? So therefore, when you're doing studies, looking at dependency is very informative, but you always have to be careful of confounding factors. Okay? Now, let's practice for your next exercise. You're going to conduct a study to see if there's a positive dependency between how much you study and the grade you receive. Now, try to solve this by hand as much as you can, and then find a correlation using Python. So find a correlation, and then you want to do a quick linear regression to draw the best line possible. Okay, this one you can do it with sklearn. Right. So that's the final exercise for correlation. Now we're going to move on to part 2. Normalize mutual information. All right, let's compare mutual information with covariance. So previously, today's class, we talked about covariance, right? This is the equation for covariance. It measures linear dependence when you have something that looks like a line, like linear dependence. It's easy to calculate, and it easily measures both data that are continuous and discrete, so it will work for both. Now, we previously, from information theory, learned about mutual information as well. The mutual information essentially measures nonlinear dependence. So you can say that this is superior. This is superior because it measures nonlinear. It's harder to calculate though, so that's the downside. It does more, but it's harder to calculate. It measures discrete data pretty easily. But if you have a continuous data, then you have a problem because from the data, you need to make sure you get P of X, P of Y, and P of X, Y, right? Before you need that to calculate the integral. And getting these distributions accurately is not easy necessarily. So mutual information is more powerful, but simultaneously it is also more pain. More pain more annoying to calculate. Okay, so very often in science we just stick with this one, but in more advanced machine learning we do use mutual information a lot more because it's just more powerful. Okay, and like covariance, mutual information suffers the same problem in that we don't know what is large and what is small, right? So what we'd like to do is we'd like to also normalize mutual information between 0 and 1. Now, covariance goes between -1 and 1, but mutual information is only 0 and 1, okay? Because it measures non-linear. It could go like this, so it's some up, some down. So you only need 0 and 1. And what we like to do is use the exact same trick that we learned from covariance, right? So the trick is couplefold. We know that the mutual information of x and y has to be lower than the dependency of xx. Once again, it's because you cannot depend on any other variable more than basically yourself, because ideally you're in accordance with yourself. Similarly, the mutual information xy also has to be lower, always lower than the mutual information yy. So the same logic follows. Therefore, this must be between 0 and 1, and this also must be between 0 and 1. When we multiply them together, we have the value that's between 0 and 1. And if we simply take the square root, it's still less than, resulting in the equation for mutual information normalized. So we take the original mutual information and we divide by the mutual information of XX, mutual information of XY, and this is how we normalize it. This value will always be between 0 and 1, and therefore it's easy to interpret the number. All right, so here's the solution actually. For your next practice, you have two data sets, X and Y. You want to calculate the mutual information by hand as much as possible. So give that a try. So what is the mutual information between X and Y? And then calculate the normalized mutual information. After that, write your own function so that you have your own function that takes X and Y and calculate the mutual information between them. So now you write your own Python function that calculates mutual information and normalized mutual information. And finally, you can compare your result with Python's. Python also has normalized. So in the future, when you just want to measure the dependency between two variables, then that you can just run this in Python. Okay, so here's the solution. Hopefully you have no problem getting it. Okay, so that's basically it. I will see you in the next lecture.